So far, all of the integrals that we've talked about evaluating have been what are called proper integrals. If there were limits, they were nice, finite numbers, and we never tried to have a discontinuity in the function that we were integrating. So there are two ways to make your integral improper. One is to give it, have limits on the integral that are infinite. So you could have either positive infinity or negative infinity, or even both on your definite integral. That makes it an improper integral. The way your integral could be improper is if somewhere on the range, somewhere on the domain of integration, you have a discontinuity in your function, specifically an infinite discontinuity. So we're going to start with integrals that have a limit, that an upper or lower limit, a definite integral with an upper or lower limit that is infinite. So typically what we do is we pretend that that limit is not infinite. We substitute some variable for it, and then we take the limit as that variable tends toward the original limit, infinity or negative infinity. So if I had the integral from a to infinity of f of x dx, I could try to evaluate that limit by taking the limit as b goes to infinity, the integral from a to b of f of x. So notice I've replaced the infinite limit with a variable, and I take the limit as that variable tends toward infinity. So I can do something similar if I have negative infinity as my lower limit. Just notice if I have both negative and positive infinities, my lower and my upper limits, I'm going to split up the integral at any convenient place, any convenient number that I want. But then notice each of these two integrals that I have here, I would want to rewrite using these two techniques that you just saw. So notice that this work is going to require combining everything we know about limits with everything we know about integrals. Some important words to know before we get started. If you rewrite your improper integral using a limit expression and you try to evaluate that limit and you find a limit, then the original integral does what we say it converges. And the answer, the result of that integral, is going to be that limit that you get. If you try taking the limit and you don't get a limit, the limit does not exist, or the limit is positive or negative infinity, then we say the original integral diverges. So here's an example to get you started off. This is a very important integral to spend some time thinking about. Does the integral from 1 to infinity of dx over x converge or diverge? So I'm going to try one of those techniques from above. I'm going to take my infinite limit, which in this case is the upper limit. I'm going to replace it with a variable, my choice. So I'm going to say that this integral, the integral from 1 to infinity of dx over x, is the same as the limit as b goes to infinity of the integral from 1 to b of dx over x. That's the same as saying x to the negative 1. So can I find this antiderivative? Oh, it's better to call it 1 over x right now. I'm going to recognize that that's the limit as as b goes toward infinity. What's the antiderivative of dx over x? It's the natural log of the absolute value of x. And I'm going to evaluate that from 1 to b. So you can see here the next two problems are printed in the way, but I'm going to keep working on the next line down. That's going to be the limit as b goes toward infinity of natural log of b. I can take those bars off because if b is infinity, obviously b is positive. Its absolute value is going to be positive minus the natural log of 1. It's going to be the limit as b goes to infinity of natural log of b. The natural log of 1 is 0, so that part's not affecting my result. And now I have to ask myself this question. What is the limit as b goes to infinity of the natural log of b? And lots of ways to think about this. I like to think back to my function booklet and think of the natural log, that's the natural log function, right? As the input tends toward infinity, what tends toward the output? What does the output tend toward? That's what I mean. So it's not going very fast, but as x approaches infinity, my output is also approaching infinity. So this limit is infinity, so that limit does not exist. So the answer to their original question, this integral diverges. All right, so for this next example, I'm going to try to figure out what I can do to replace that upper limit. I have an upper limit that's infinite right now. So good to think about, just to foreshadow what's coming next. Notice that I don't have the second problem, which is, do I have any discontinuity in my integrand on the interval 0 to infinity? So when I think about factoring that integrand, x squared plus 4x plus 3, that's x plus 3 times x plus 1, which has two roots, but the two roots are -3 and -1, which are not on the interval 0 to infinity. We're going to see plenty of problems where that comes up, but that's not what's happening here. What's happening here that makes my integral improper is I have infinity as my upper limit. So what can I do? I'm going to rewrite this as a limit. This is going to be, okay, and while I do that, I'm going to come over here to the side first. I notice I'm going to have to decompose this big fraction into the sum of smaller fractions. This is a partial fraction decomposition problem. So I'm going to do that first, and then I'll go back and rewrite my integral. So I know that 2 over x squared plus 4x plus 3 is going to equal a over x plus 3 plus b over x plus 1. So a times x plus 1 plus b times x plus 3 equals 2. So ax plus bx equals 0x. So a equals negative b. And I know that a plus 3b equals 2. A is negative b, so negative b plus 3b equals 2. 2b equals 2, so b equals 1. And a is going to equal -1. So now I'm going to use this to rewrite my original integral. So this is going to be the limit as b goes to infinity of the integral from 0 to b of, I'm going to write this as the sum of two fractions, dx. So my a, I said, was -1 over x plus 3, and +1 over x plus 1. Now I'm going to find an antiderivative. I'm going to have this limit as b goes to infinity out here waiting its turn to get evaluated. So that's the limit as b goes to infinity of negative natural log of x plus 3 plus natural log of x plus 1, all evaluated from 0 to b. It's going to be the limit as b goes to infinity of a couple ways we could go from here. So negative natural log of b plus 3 plus natural log of b plus 1. Again, I don't need those bars. Minus negative natural log of 3 plus natural log of 1. That's going to be the limit as b goes to infinity of the negative natural log of b plus 3 plus the natural log of b plus 1 minus, so plus natural log of 3 minus natural log of 1 is 0. Natural log of 1 is 0. So the question is, am I going to be able to simplify negative natural log of b plus 3 plus natural log of b plus 1? That's the same as the natural log of, again, I'm not going to need those bars. Everything here is positive. That's b plus 1 over b plus 3 plus natural log of 3 I'm taking the limit as b goes toward infinity. So that's the trick there, is to recognize that when you have a negative natural log, I can make that negative the exponent on that thing that's getting natural logged. So I can end up rewriting this as a quotient. Now when I take the limit as b goes to infinity of b plus 1 over b plus 3, that's just 1. This is going to equal, it's going to equal then the natural log of 1. Because as b plus 1 goes, as b goes to infinity, b plus 1 over b plus 1, that simplifies, right? To make the natural log of 1 plus the natural log of 3. Natural log of 1 is 0, so final answer, natural log of 3.